Okay, so we're going to start with class 17, and this is the beginning of, I believe we're in chapter 11 now. And so this is part one of lift and drag. And here are cartoons where we're showing some lift and drag. We got Wedded on a hang glider, and here he is going, trying to walk towards the fan that's causing him drag. The hang glider actually has both lift and drag on it, by the way. Interesting. So here's some pictures of some things that are in the midst of lift and drag. I kind of liked this one because it had the clouds look really cool with the little vortices that are coming off of the wingtips. And here we got a stealth fighter. Of course, that has both lift and drag. We have a wind turbine that has lift and drag as well. On the foils, right? There's the foil shape right there that causes lift and drag, and some wheat. I don't even know why that's there. Other types of lift and drag that we would be concerned with. All right, and so we're mostly focused on drag in this class, in class 17. And there's kind of an interesting comparison of old cars versus newer cars, and the difference in horsepower that's we've been able to reduce the amount of horsepower because of aerodynamic drag. And aerodynamic drag is enough to knock a tree down, as we've learned in recent hurricanes. So these topics are relevant in lots of different ways for us, especially in aerodynamics and hydrodynamics. Where in aerodynamics, we do airplanes and golf balls and buildings and sailboats above the waterline. And we also are concerned with hydrodynamics, which also will affect mostly drag, but there are some instances where we will have a lift in hydrodynamics, like hydroplanes and that type of thing, with they have the appendages below the waterline. So ship hulls and those appendages, like, rudders and that type of thing. And there's actually, and they could say that those also will produce lift as well as drag. Torpedoes, submarines, and then sailboats below the waterline, and some fancy keeled sailboats have little wings on them. Provide some stability, but also it could be a certain amount of lift. So in the flow scenarios that we often will see on the left, we might have a body that's moving through a stationary liquid, or we might have a stationary body with liquid flowing around it. Or we might have the combination. We have liquid moving and bodies moving. We usually treat all of these when we're doing an analysis as being the same. So even when we're modeling something, like in a wind tunnel, might be an airfoil that would be on an airplane that's moving, but we keep the airfoil stationary and we move the wind past it. So there's really two parts to this lift and drag, and we want to try to keep that in mind all the time. There's two elements. We have pressure, drag, and lift. And remember that pressures, those pressures are always acting normal to the surface. And then we have shear stresses that are acting on the surfaces, and those are acting in line. So down here in this little generic little differential little piece of area right here, we could see that the pressure times the differential area is acting perpendicular to the surface, whereas the shear stress on the wall, I think that's what the W is for, times the incremental area is acting in line with it. And this is an arbitrary thing with, using this angle right here to provide a side convention. So this one plus this one equals this one diagram is one should be very helpful, stuck in your head. And that pressure can be negative as well as positive. And that negative pressure on the top is one of the elements that's producing lift right here. But you could also see that there's pressure on the front right here, and that's producing drag, that pressure aspect. The shear, we might not mostly associate that with some amount, with the drag, but actually shear can produce some lift. Right? Just by way of the sign conventions, we generally consider that the lift is going to be completely vertical and the drag is completely horizontal. for wings when we're talking about there. But we might want to think about that if we're maybe we rotate the thing and maybe it's in a liquid or something along those lines, or maybe it's a sailboat, right? Where the sail is sort of the you could think of that as the wing kind of shape. And then, of course, what we would consider lift isn't in the vertical direction, but that's neither here nor there. So, if we could figure out what the distribution of this pressure was, like exactly, and we could figure out what the distribution of the shear stress were, we'd be able to quantify this lift and drag. But it's hard to figure that out. So we'll talk a little bit about boundary layer flow. I don't want to get too far into it. But I do want to have it sort of introduced, and so you have some basic background in that. I might do that in video part 2 because it's a little bit longer than I really want to put in one video. But if we were to integrate to find the drag on this arbitrary type of scenario here with this plate, we would take the integral of all these incremental forces, and that would be, we could find that by breaking that down into the integration of all the pressure times the cosine. In of course, we're using this angle right here for the sines in here, and we can see that the shear is times the sine right here. So what we've really just done is try to keep this thing, try to see where the horizontal components of that pressure times the area and that shear times the area. And then here for the lift, you can see, well, in this case, we have the pressure is actually going to be a negative, but that's just because the orientation of this arbitrary little area right here. And you can see that the shear could actually be positive because in this instance right there. So let's take a look at more of a wing type of shape, or here you go for another arbitrary angle. So this is more of the kind of the angle that we're thinking about seeing in a typical lift and drag type of situation if it applies to an airplane wing, where the angle of attack, and we even see this up here, these angles, that the lift and the drag are sensitive to what the angle is with respect to the flow direction. Remember that the pressures are perpendicular to the surfaces and the shear stresses are in line with the surfaces, and that pressure and shear stresses can contribute to both lift and drag, and they might be detrimental to one of them or the other, but they can play a part in both of them. So you might want to consider what the special cases of 0 and 180 are going to be for both the lift and the drag, right? So there's really going to be 0 amount of lift taking place at 0 degrees of angle, and there's really going to be 0 lift at 180 degrees of angle. And at 0 degrees, entirely, pretty much, it depends how thin this is, but almost entirely the drag is going to be due to the shear instead of the pressure. And then at the 180, the drag is really going to be entirely due to the pressure instead of the shear. So in that mindset, and here's like a diagram out of Sengel showing that, like, here's like a little plate right here, and that's in line with the flow, and this is really going to be shear drag that would be created right here, but then you turn it 180 degrees, and now this is going to be pressure drag that's on there. This other piece is something we do quite often, and that's going to be a cylinder or a sphere in a slow stream. And spoiler alert, these are usually the two extremes that we look at the most often. We have a streamlined body and what we might call a blunt body. And this one down below is also sort of we could consider that a blunt body. And just more pictures from Sengel where we have some distribution of these pressures and shears resulting in this net force, the resultant force, which has the components of lift and drag on it. Another pretty picture. And just emphasizing that we can have negative pressure on the top, and that's going to be one of the large things that's contributing to lift. So I'm at the 9-minute mark. Keep going. So we're going to start talking about this thing called a boundary layer. And a boundary layer is formed when an object is moving through, or a liquid is moving around it, and we usually consider that the thickness of it can be this del, and kind of measured where the far field upstream velocity, when we get to about 99% of that, and we'll see that in the next figure here. And the viscous effects within the boundary layer are important, but most of the viscous effects outside the boundary layer aren't, right? So it's sort of like this definition of the place or the region around the object that's in a flow field where the viscous effects are taking place. And when you have large Reynolds numbers, you end up with getting a thinner and thinner boundary layer. And so sometimes we'll use the phrase boundary layer flow, and that means that's a flow where the boundary layer is significant enough to matter. And so it's really going to be for Reynolds numbers that are greater than 1,000. That's sort of like the unofficial, I guess maybe somebody might make it official. It's sort of the range at with which we start talking about the boundary layer really mattering. So here's the idea where a boundary layer is starting to develop. And so this is like an infinite plate where the flow is going past it, and it starts right in here, and the boundary layer starts increasing its thickness, and then it gets to a certain place where it ends up being fully developed. And the thing that we really care about, one aspect that we should keep in mind, is that original definition of viscosity. And that viscosity, the definition, I'll switch over to my camera so I can write this down somewhere. Recall that the original one that we had in maybe the first day of class or the second day of class, we had shear is equal to this right here, where we said we had du dy. And what we meant by this is that this describes the slope of the velocity field, right? So I guess I could show it like right on here. So that slope right there, or the slope as you move up, right? So the slope isn't the same everywhere along inside that boundary layer. That's what if we can integrate this right here, we can figure out where the shear forces or shear stresses that are taking place. And right, so the shear forces are in this direction, and of course they're divided by that area. So we move back over onto here. So that boundary layer develops, and when it can be fully developed after enough span along the length of this plate. And if we could know that velocity distribution, we'd be able to figure out what those shear distributions are. So we usually generally categorize our flows in two broad ones. Let me say two means of categorizing. So we have the two regular objects to consider, and then two zones that we consider. And so the two objects are the streamlined body and then the blunt body. And then the two types of flows that we consider are laminar and turbulent. Right here. So we'll start just talking about the laminar turbulent and then introduce the idea of the turbulent. So here in the streamlined flow, we can see that we're mostly going to be concerned with the shear taking place. And if we have very, very low Reynolds numbers, we want to remember that Reynolds number is a non-dimensional number, and it is in its sense a ratio of forces. And on the top, we have inertial forces, and you can see that we have, density times velocity times a length, where that density is like a mass, and the velocity of mass times velocity is momentum. So we have those types of related forces, momentum-related forces on top, relating to inertia. Where on the bottom, we have viscosity, and those are really like shear forces, viscous forces. And for a very small Reynolds number, that means that the viscous forces are much larger than the inertial forces. But as we get increased speed and increased Reynolds number, the boundary layer starts to thin, and then it starts to develop. And now the viscous forces start to really matter inside this boundary layer. And by the way, they said like 1,000 up above, like we set up here. 1,000 is where we really start to say that the boundary layers really start to matter. So up here, the boundary layer really didn't kind of matter all that much. It was really the inertia forces. Excuse me, I said it the wrong way. Yeah. Yeah, I think I said this backwards just a minute ago. I'm sorry. The viscous forces matter here in this zone, and then the inertial forces start to dominate. Right, so dominated by inertial forces when we have the thin boundary layer. For a blunt object, we have a lot more complicated things taking place, and for in the smaller, if it's not, we usually refer to this as being streamlined. So here's a streamlined body, but if it's not streamlined enough, we start to have something called flow separation. That starts taking place, and we will have a different phenomenon that we have to look towards, where we get to maybe the Reynolds number about 50, and we start to get that separation, and then we actually have this like recirculation, separation kind of bubble thing that's happening behind it. And if you go up high enough, that the boundary layer separation point starts moving backwards, and then we start to get this turbulent zone where we have this wake region, and we have the viscous effects are negligible except in the thin boundary layer. So streamlined and blunt bodies are typically act similar to either a flat plate or a cylinder, and the blunt, right? So we can kind of like have those two different categories of bodies, and then we could have the two different categories of flows, which are laminar and turbulent. I'm going to wind this down here in a moment. Maybe I'll go ahead and soldier on through because we're not going to do too much more with these topics in this in this class. We're going to pick them up a little bit more when we get to the Navier-Stokes and CFD, and then again when we're doing piping stuff. So if we have on this infinitely long plate right here, we start to take a look and analyze this boundary layer thickness where we're starting to develop. And instead of using a Reynolds number, which generally what we've been doing is having a Reynolds number, let's see, I'll write it. Here's like the Reynolds number for something that's a circular piece right here. But now we're going to have a Reynolds number that's going to be based on its location along the length, right? So we kind of look for the Reynolds number is going to be changing as we come along through this boundary layer. And there's this laminar to turbulent location that can form. And we could kind of try to figure out where that is, where we make the transition from a laminar boundary layer to a turbulent boundary layer. And inside that turbulent boundary layer, we can think of that as being chaotic, where we can do some analysis within the laminar. There is some amount of prediction that we could make about how that viscosity is going to behave and how what the velocity profile is going to look like, or we can make an estimate of what the velocity profile is going to look like. But when we start getting into the turbulent boundary layer, we have all bets are off, and we have chaos in there, and we have to start coming up with models. And there's lots of models, and that's closely related to what has to take place in computational fluid dynamics in order to solve for things like drag and lift. Using that computer code. So it's kind of important that we make this distinction between where these zones take place and the kind of category of flow that we need to be interested in. But you can see the critical location can be anywhere between 200,000 and 3 million of the Reynolds number as it relates to this position. I should say that not all Reynolds numbers can be comparable to each other. We have to compare the like one in the sense of how we're using it. And this one with the subscript X, that's a Reynolds number that's describing something that's changing as the flow starts to develop. So let's see, we have two more parts to this discussion at the 19-minute mark, where we want to talk about like some flows that have some people that have actually solved some things related to the boundary layer thickness and the wall shear stress. And these are just two examples. And we haven't really covered the Navier-Stokes equations, but we will soon. And we will highlight the fact that we can't really solve them with a closed form solution, except in limited situations where we set a whole bunch of constraints. And one of them was done by Prandtl and Blasius, where we went ahead and we came up with the solution where we assumed laminar flow only. And so you can see the Blasius has this distribution right here. So this distribution, this little chart right here is a velocity profile approximation. And there's the approximation that Blasius made right in there. And that enabled him to solve the Navier-Stokes equations. And one of the fallouts was he's able to predict what the thickness, and that's what the del is, of the boundary layer throughout as you're moving along in the x direction along an infinitely long plate. And then he's also estimated what the shear stress is going to be. These are closely related. We're not going to do the derivations of them, but you can you could get a sense that we are able to do it because it's closely tied to the velocity profile. Now, another simplification that we could make to try to solve these Navier-Stokes equations, which we haven't seen yet, is to have a linear velocity profile. And so here's one where we have this momentum integral boundary layer equation for the flat plate, where now we say the velocity layer profile is linear. And for that one, we have a boundary layer thickness predicted to be 3.46 Vx over the velocity, square root of that. You can just compare that to Blasius's. And we see the wall shear. We have a coefficient out in front of 0.289 with this the velocity to the 3/2. You can see that we had 0.332, and these are just two. These are just two solutions to these Navier-Stokes equations in order to investigate the boundary layer. But once again, these were both for like laminar conditions and only for a infinitely long assumed flat plate. That's one of the reasons, and because of the complications of trying to solve stuff inside the boundary layer, which are closely related to that velocity profile, it's one of the reasons why we need CFD to solve more complex problems. So I think I butchered that, but we'll hopefully, by way of example, get a better sense for the interaction of the boundary layer and the things we want to find from it, which are principally for us are going to be the lift and the drag.